Hi Kepler, this is Mark again, and I'm going to talk a little bit more about yogurt specifically and about what a physicist thinks about what phases are and what the difference is between a solid and a liquid and a gas. So I'm going to draw some stuff on this whiteboard here and think about, okay, what is it that we mean when we say liquid? What does it mean when we say solid? And what does it mean when we say gas? So solids, we tend to think of them as being things that have shapes and they stay in their shape without changing. And they can be balls and they can be squares and cubes, but they don't flow. They don't change their shape. They're just solid. And then we've got liquids. Liquids do change their shape. So classic liquid is water, and we notice that liquid will, like water, will fill in a cup, and it will change shape. So if I pour that into a different cup, like a smaller, like a thinner cup, that water will fill in higher so that it can have the same amount of water in there, but the shape is different because the shape of the container it's in is different. And then there's also gases, which even more than a liquid will really change shape. So like if I put a gas inside a certain box and it's got a bunch of things inside it, like a whole bunch of little tennis balls or something like that bouncing around, and then I change that to a bigger box, then that same gas will spread out and completely fill the container. So the classic things we talk about that tell you that something's a gas is if it will fill whatever container it's in. It'll spread out. A liquid will change its shape to match whatever container it's in, but it doesn't change the amount of stuff that's there or the total amount of space. If I was like to count up how much space is there and how much space is there, those two are the same amount of space. This one, the gas, it takes up a different amount of space if you change the container. And solids don't change their shape at all. All right. So what is it about a material that determines whether it's going to be a solid or a liquid or a gas? And thinking about water is really important there because it's a material that we're really familiar with, and we know that when it's a solid, the reason it's a solid is because there's individual water molecules that line up and match together in a particular shape. It's because there's connections between all of those molecules that hold it together so that it won't change its shape even if you push on it. So that's ice. And liquid water, those same molecules are moving around. They're not locked together, but they still kind of interact with each other. They, like this one will pull on or push on the other ones that are near it in a way that causes it to flow together so that it won't separate into lots of little pieces. It'll flow. And then in a gas, those molecules are so spread out and they're moving so fast that they really don't interact with each other at all. So this one doesn't really pull on this one over here, and this one doesn't pull on that over there for the most part. And that's why they're able to fill in whatever container they're in, because they can just keep moving. So this was ice over here, this is liquid water, and this is steam. And maybe you know all of this already, and I'm just filling in some details. So the thing that determines whether a bit of water molecules are currently in water form or in ice form or in steam form is basically how fast they're moving. If they're moving particularly fast, then they can't form any of those attractions with other molecules, and so they're steam and they can fill in any container you put them in. And if they're moving kind of a medium speed, then they do interact with each other. They grab on and they hold, but not very tight, and that allows them to flow in a liquidy sort of way. And when they're in ice form, they're moving really slow, and they form up and they line up into this pattern so that they can't get away, and that's what allows them to keep their shape no matter what. So that distinction between different phases of that same material really makes sense for water. But here's the funny thing about it. It really doesn't make sense if you're thinking about a small number of water molecules. This is one of the things that's important about the way a physicist thinks about this. It's not just like this molecule is in water form, and that molecule right there is in ice form, and that molecule there is in steam form. Because some of those water molecules are moving really fast, and some of those steam molecules are moving really slow. Slow enough that if there were other ones that were also moving slowly, it would form up into water form. And some of these ones are moving fast enough that if they had a chance, they would move into steam form. And those properties that we notice about a material that we call ice, water, and steam, you can really only see those properties if you have thousands of those molecules, many thousands of them really, before you start to see things that really look like solid ice and look like liquid water and look like steam gas. Basically, one water molecule isn't wet. One steam molecule isn't steamy, and one ice molecule isn't solid. They're all identical. It takes thousands of them for it to behave like a thing that doesn't change shape, or like a thing that can change shape but not volume, or like a thing that can change shape and volume because it can fill in containers. So when you asked me that question about yogurt, you were noticing something interesting about it, which is that it seems to have little bits of the properties of solid and properties of liquid, though not really steam. So what are the yogurt properties that seem liquidy? It flows. It can fill in containers. It's kind of like the silly putty in some ways. Like it's slow, but it does move in a way that fills in, that can change shape. But also, if you look at it for a short amount of time, or if you leave it in the fridge, or if it's in the container, it really seems pretty solid too. It's more like Jell-O. It seems like it has a shape, and you can dump a chunk of yogurt out of its cup, and it will keep its shape for a while, and then it will eventually start to flow the way that a liquid does. So what is it about yogurt specifically that makes it have both of those kinds of properties so it seems like it's in between? So you should look up what's in milk, or what's in yogurt, sorry. It's not just one thing. There aren't molecules of yogurt. Yogurt is a mixture of some water and some fat and some other stuff that makes it kind of thick. And when you mix more than one thing together, then it behaves differently than either of those things by themselves. So if you take some water and then you mix in some fat particles that are kind of suspended around in between all those water molecules, so you've got a bunch of each kind together. It's actually mostly water, but there's enough fat in there that it seems pretty dense. Put all that together and it behaves differently. It starts to shift from being liquid towards being more solid. And that's really interesting. So part of my answer to your original question is, it's really not either one. It's a little bit liquidy and it's a little bit solidy. And exactly which side of that divide it's on kind of depends on exactly how much fat is in there, and exactly how much water is in there, and what temperature it is, and how fast those molecules are moving. And those properties kind of tell you which one you should classify it as. But I think it's more interesting to think about how it does behave and why it behaves that way than it is to be able to say, oh, it's just a liquid or it's just a solid. Another example that I like to think about that's really similar to this is sand. If you take a bunch of dry sand and you pour it out, it behaves kind of like a liquid because it can fill in a container. But if you have lots and lots of sand, then the middle parts of it behave a lot like a solid because they're so tightly pushed by all the sand around it that they don't move. They keep their shape, but the stuff that is closer to the edges is more like a liquid. But then if you mix a little bit of water in with that sand, so you've got a mixture kind of like the yogurt, you get some really interesting properties. Like if you're on the beach and you're running along right near the water line where the waves start to go over the edge of the sand, that sand right there, if you run over it, it feels almost like concrete. It's like really hard. But then if you stand in that same spot, you will slowly sink through the sand because it behaves more like a liquid if you're sitting on it for a long time and slowly. But if you're hitting hard, then it feels more like concrete. So there's lots of examples of materials that behave in some ways like a solid and in some ways like a liquid. And it's really interesting to think about what is it about them that makes them be in between. And for the example of yogurt, it's really because it's a mixture of more than one thing that has those odd properties. Maybe something you could think about is whether there are any examples of things that behave in between these two, that are between the liquid and the gas, just like the yogurt is in between the solid and the liquid. So thanks again for this question. It was really fun to think about it, and I hope you send me back some more questions. Tell me what you think about the silly putty. Which one is that? Is it solid or liquid?